In this video, we'll talk about the application of Newton's laws. And I did not talk about the usual application like in 1D motion, other regular two-dimensional motion. I'm going to talk about several special motions that we need to pay attention to. And the first one I want to talk about is the property of the string. So what are the things that we need to be thinking about when we talk about the string's property in terms of Newton's laws? And so let me first draw a string here. Let's say there's a section of the string. But again, don't be confined by the name string. It can be also rope, cable, etc. Okay, so that's the string, and we want to study, let's say, a small section of it. But now, let's say on the left side, there's a force, let's say T, let's call this T left, and that's force T right, okay? So now our focus here is to figure out the property of the string about its tension force. What's the tension force here? Specifically, what is the relation between TL and TR? Okay, now before I go into detail, the reason we want to talk about this tension force is because, let's say we're looking at one question here. Let's say there's a string attached to an object and putting the object on a surface with some acceleration A. And then there's on the right side here, there's your hand, your pulling force here, and then on the left end, if you think about the object as this block here, then we want to talk about the tension force applied on the block by the string. Okay, but now we know the tension, the pulling force is F. Now, can we get any relation about T and F so that we can apply that to study the block's dynamics? So, so that's why we need to talk about the string's property before we can identify the T's expression. Now, to talk about that, let's say this string here has acceleration A, just like in this case here, and we're looking at a small mass delta M of the string. And if I draw the free body diagram for this small section delta M of the string, then let me call the right side here T2, and then the left side T1. So these are the two forces acting on delta M, and that would be the free body diagram for this delta M. So according to Newton's second law, we can write down T2 minus T1 equals delta M times A. Now, since we know the string here accelerates together with the block, so this A should be non-zero. And also it's positive, right? Because we when we write down T2 as positive, T1 as negative, we're assuming that the right side is the positive direction. So A should be positive. Now, according to this, I can safely say T2 is greater than T1. Okay, so T2 is greater than T1, and then the amount of the difference is the delta M times A. Or you can say T2 is greater than T1 by this amount, delta M times A amount. Okay, so now I can do this also for the problem here, where I consider the whole string its mass m, okay, little m, and I can say f, according to Newton's second law, f minus t on the left side equals ma, and then we need to include the string mass in our calculation. Okay, now that is reasonable. You can do that. However, when we talk about this actual example here, we usually have the condition that the mass of this block is much greater than the mass of the string. So string's mass is negligible. Or you can say delta m is almost a 0. Okay, so that's why I want to add some condition here for the string. So usually we don't want to go into the trouble of writing down the mass of the string, of the rope or the cable. So we're going to say it's ideal string, ideal rope, etc. And that would mean the mass here is almost a 0. Now, usually questions do not specify this, but if you see the question says ideal string, then that would mean this. The mass of the string is 0. Okay, but if the question didn't mention at all the mass of the string, then you can safely say you're looking at ideal string. Okay, so that's the property of the string. Now, when we study dynamics, another device that you usually see is the pulley. So that's why I'm going to talk about the Pulleys property. And very much like the strings case, we're going to talk about ideal pulley. So what's the meaning of ideal pulley? It means that the mass of the pulley is almost a 0. So you can neglect the mass of the pulley when you do the calculation for a problem that involves pulley. And another condition for ideal pulley is that it does not introduce any additional force. So let me show you first a picture of the pulley. So usually it's like a round disc, and then there's a fixed axle here, hanging the pulley to some ceiling. Okay, and then there's a string going around. The pulley. So you can rotate this disc by pulling it down. So let's say we apply pulling force F downward on the right side, and then on the left side, the string is tied to, let's say, a block with mass capital M. And then we want to figure out the tension force Again, mass M here, the block M here is usually the object you want to study, and then you want to figure out what's this tension force. Now, for a regular string, we know on the previous discussion, F equals T, right? If we think about the ideal string here. So now that condition will come in here for the ideal pulley. It will also mean the mass of the string or mass of the rope is almost 0, so you don't need to consider that. However, since we added this pulley here, will that make this condition, the relation between T and F, different in our situation here? And we're going to say that for ideal pulley, this relation still holds. So we can still say T equals F. Okay, but why? Now, in the future, we are going to talk about the rotational dynamics. So if you pull down the pulley in this direction, it means that it's going to rotate this way, and that is also going to introduce some angular acceleration alpha. And here is a side note. You don't need to fully understand this because in the future we're going to repeat this again, talk about rotational dynamics. Okay, so there's a torque on the pulley. Now suppose the radius here for this solid disk is R, then the net torque acting on the pulley with respect to this rotation axial is sigma tau equals F times R minus T times R. Okay, so the difference between the two sides of the pulley, this force is pointing downward, and the tension force from the string is on the left side downward, and the pulling force is right side downward. Okay, they each introduce a torque around this axis, and the pulling force introduce a bigger torque. So that's why we do this subtraction here, and that equals so-called rotational mass times alpha. Okay, and this I here is proportional to the mass of the pulley. Now, if the mass of the pulley equals zero here, that would mean I equals 0. So that would mean F equals F equals T. Okay, so that condition, if pulley mass is almost 0, then F equals T. Okay, so in that case, we should have this condition, but it's under the condition that the pulley's mass is almost 0. Okay, so let's summarize the ideal pulley condition. The pulley of the mass is 0, and then the string's mass is 0. Then we have this device here, transfer the pulling force F exactly to the mass M here to pull it up. Okay, all right, so that lead to our next topic about fixed pulleys. Okay, so there are two kinds of pulley setup that people use to move objects, and the first type is the fixed pulley. The picture looked exactly like the one we saw earlier, but let me redraw this picture. So that's kind of rotating disc, and then there's a fixed stick here connect to the center, and that forms rotation axis, so the disc can rotate along this center. Okay, and the right side of the string is pulled down by a pulling force, and then the left side here, the string is connected to the object that we want to move. Now in this case we call it a capital M. Okay. Now for fixed pulley, what is the property of the, let's say, when we pull down the string, the object moves upward. So what's the property of the displacement of this object compared to the string's movement? And also the force, what's the relation between the force? So the force, we already talked about that, right? So the properties of the fixed pulley. First one, the tension force. Let me first draw a picture. The free body diagram for the mass M. That's tension force, and the other force acting on M is gravity. Okay, so first is the force relation, T equals F. Okay, and second property of the fixed pulley is when this object moves upward. Let me use a different color here. So this object M moves up, let's say delta x distance. Okay, now the right side, the string need to go down by the same amount. Okay, so the force here need to pull down delta x, also delta x distance. So the object displacement, let's call it magnitude, since their directions are different, equals the string displacement magnitude. Okay, so these are the two properties of a fixed pulley. Just a little bit more discussions of these dynamics. So now if I think about the free body diagram for the object M, then from there I can build a coordinate system. Let's say this direction is the positive x-axis. Okay, upward is positive x-axis. Then we can write down Newton's second law. The net force along this direction equals tension force is positive, gravity now is negative, equals ma. Okay, so you want to write down Newton's second law like that. And if you want to write down the relation between T and F, then it will be T equals F. Okay, so these are the two equations you can write down for solving the object's dynamics. A bit further, so in the future when we talk about work done, okay, so you can skip this part of the discussion if you have not studied the work. It's a future topic, okay, we're going to cover. So work is equal to force times the displacement. Okay, now in this case the tension force equals pulling force, so we the work done in object equals T times delta X. Okay, we have that, right? Now, if you pull up this object with a constant velocity, so let's add more and more condition here. Constant velocity, which means that A equals 0, okay? Then we can calculate the work done by the force F equals mg times delta x, okay? So mg is equal to the tangent force from this equation. Okay, so that's why the work done by the pulling force is equal to the gravity times the displacement. Okay, and then later on we're going to compare this work to a movable pulley. Okay, so that's the next topic. So now what's the movable pulley? Let me first draw a picture to build such a device, and then we can talk about the property of it. So now let's say a string, right, tied to the center of the pulley, and then there's an object hanging here, and there's a pulling force F on the right side. Okay. All right, so let's call the movable pulley. It means that the pulley moves together with the object that we want to pull it up. All right, so now just like before, we need to talk about the like different property, like the tangent force relation with the pulling force, and then the object displacement relation with the string displacement. And then later on, we can talk about the dynamics equation that you need to write down, and also the work done by the pulling force F. Okay. So first, what's the properties of a movable pulley? Now we still have that ideal pulley condition, meaning the mass of the pulley is negligible. So let me write this down. It's almost 0, meaning when you compare to the mass, capital M, is negligible. That's very small. So if I draw the free body diagram for this mass M plus the pulley, okay, because the tangent force is acting on the pulley, it's not directly acting on the mass M, so that's why we need to add the pulley in our system. Then we can say the force F is acting on the object M. Okay, so that's the force we already have here. That's F acting on the system. On the left side, there's a tension force T. Okay, and then the gravity here still acting on the mass M. And that's it. That's the free body diagram for M plus the mass M plus the pulley. Now, what are the properties, right? So we need to figure out the T and F relation. So just like before, T equals F, okay? And the reason for that is because the same string, right, go around the pulley, and we should have the same force on the same string especially when the pulley's mass is negligible. Okay, so remember, just like before, we need to argue that the like here, right here, yeah, we need to argue that when we accelerate the pulley in these rotational dynamics, because its mass is negligible, so there's more rotational mass equals 0, and then the pulling force equals the tension force. Okay, so the same thing happens here. All right, so that's the and you may ask why this capital M does not contribute to that dynamics. The reason for that is because the force due to the mass M is this tension force, right? That's the tension force at the center here, acting on the pulley, and that tension force has 0 torque. Okay, so torque due to this interaction between the mass M and the pulley through the center of the pulley has 0 torque. So that's why we still have this condition here. Okay, still have this condition. Now the second property is about the displacement. Okay, so let me draw the displacement with a different color. Let's say this mass M ascend by delta x displacement. Okay, now what will happen here to the string here that we need to pull? These pulling force need to pull out. Okay, what's the length of the string that one needs to pull out? So the left string need to be shortened by delta x, right? Because the pulley will move up parallelly in its vertical direction, so it will shorten the left string by this delta x amount. Okay, and the right side is also shortened by this delta x. Okay, they both goes upward. Now the missing 2 delta x goes in here, so we need to pull up the string on this side by 2 delta x. Then we can account for the missing 2 delta x on the left and right side of the string. Okay, so let's write down the relation. The object displacement magnitude equals half the string displacement magnitude. All right, so that's the property of the movable pulley. Now let's also finish the dynamics from the free body diagram. Now let's also say the upward is the positive x-axis. Then if I write down the free body diagram for the whole system, the object plus the pulley, then I have net force equals positive F, positive T, minus capital Mg, and that equals Ma. Okay. But since T equals F, so we can also say there's another tension T here acting on the right side. So from here we actually have 2T minus Mg equals Ma. Okay. Now from there you should be able to solve the problem to calculate the A, for example, if you know the tension force or the pulling force. Now another thing I want to mention, just like before, think about the work done by the pulling force F. Okay, so we know the work done by F is F times the displacement, right? Now the displacement is 2 delta x. Okay, so previously we said that the mass M move up delta x, then the force move, the string move up 2 delta x. Okay, so that's the displacement of the force. And that means that if I want to, again, just like before, I want to describe it as the gravity mg, then I need to do the assumption that we pull up the object slowly with a constant velocity, meaning a equals 0. Okay, so constant velocity for m will mean a equals 0, and then t equals half mg. Okay, so that's what I need here. So I'm going to plug in here, and then I get half mg times 2 delta x. So the 2 and 1/2 cancel out. The work done is mg delta x. Okay, so that's exactly the same as the fixed pulley case. The work done by the pulling force is mg delta x. So now it's again mg delta x. Okay, so it means that the work cannot be changed by the pulley device. Okay, so work done on the object by pulling force F cannot be reduced or cannot be changed by the pulley device. Okay, they're always the same, because that's exactly what happens to the mass M, right? When it goes up by delta x, the work done by gravity is negative mg delta x, and that need to be provided by some external force F. In this case here is F that does the work. Okay, so they should be equal, and it doesn't matter whether you use a fixed pulley or movable pulley, they're always the same. The same reality is that the object M move up by delta x. So something need to account for that kind of work that we need to do. Okay, but we do save the force, right? Because now the pulling force is half the mg. So that's why people still want to use this movable pulley, because if the strength or the pulling force is not large enough, you want to pull up something heavy, then you have to use this movable pulley, because it can save you half of the force. Okay, although it does not save the work. Right? Work is always the same. Okay, so that's the concept of the movable pulley. Now to end this section, I want to talk about one example of movable pulley. Now here is the problem set up. So now let's say there's a block with mass big M is tied to a movable pulley. Excuse me. Yeah. Tied to a movable pulley. And then the movable pulley is tied to one end of the string is tied to, let's say, a wall. Okay, and then the other end is tied to another pulley here. Now the difference is that this second pulley is a fixed pulley. Okay, and then the string will go down further to another mass, little m. So that's our setup. There's a movable pulley plus a fixed pulley. Okay. Now we want to neglect the friction force, so the surface here is smooth, which means that there's no friction if the object M moves. Okay, and also exactly because of that condition, there's no friction here. As long as there's a non-zero mass, little m, then the whole system will accelerate in this direction. So there must be acceleration a here, and the mass m also has some acceleration. Let's call this a prime. Okay, so you may ask me, why do I use different accelerations? Aren't they the same? The answer is not. Okay, so I will talk about why they're not the same. So that's the problem set up, and then the question asked up about how to calculate the acceleration, these two accelerations, a and a prime. A and a prime. Okay. Now, before I talk about anything else like relation between these two accelerations, let's first draw a free body diagram for the two masses. Okay, so for the little m here, it's easier. There's a gravity mg. There's a tension force T. Okay, and that's it. That's the free body diagram for the little m. Now for the big M, we need to consider the right side string. This one's like, lower side string tension force. It's T here, and another tension force T, and they're equal, right, for the region that we discussed earlier. And because the surface here is smooth, so there are no other forces in this horizontal direction. Now in the vertical direction, of course, there's this gravity, capital mg, and the tension force due to the smooth surface, which is upward. Okay. Now let's write down the Newton's second law or equilibrium conditions. And before I do that, I need to set up the coordinate system. So the coordinate system here should be set up so that the positive direction is downward for this little m. And for this big M, we need two directions. The positive direction is to the right, and the vertical direction, the positive direction is upward. So a 2D coordinate system. Okay, so now let's write down the little m. We only have one equation for it, which is net force equals positive little mg, right, because it's in the same direction as this x-axis. Negative tension force equals ma. For big M, the net force in the horizontal direction or the x-axis direction is 2t. Okay, we have t plus t, so that's 2t. And that's it, equals big MA. A prime, sorry. Now in the y direction, the net force equals the normal force, which is positive, minus gravity must be 0 here, right? Because there's no motion of the object M in this y direction. So these two forces should be in balance. So these are the two equations we can write down. But as I said later, I haven't actually argued the relation between A and A prime, but I do have some relation. Remember, when I talk about the movable pulley, I talk about the displacement of this object and the displacement of the string. Okay, now this string here in our setup is like this M, little m. So little m move down if capital M moves delta x. If this capital M moves delta x, then these two strings need to be shortened by delta x. And each of them has shortened delta x. That means that this little m here moved down to delta x. Okay, and they both start from rest, and then one move down, one accelerates downward to delta x, the other one accelerates to the right delta x. So that means that their acceleration relation is given by the following. So delta x is 1/2 a prime delta t squared, and 2 delta x is 1/2 a delta t squared. They accelerate for the same time interval, delta t. That's why from here we should say a is twice a prime. So that's the relation I want to use together with the this equation 1, equation 2. We can neglect this one because it doesn't help the calculation of a or a prime. But we do need a equals to a prime. That's our third equation. Okay. All right, so now let's see, how can we solve for these two a's? Gravity, the little m here and big M, they're known quantities. T, however, is unknown quantity. So let's think about getting rid of this capital T. Okay, and this capital T is related to a prime here. So we have three variables, a prime, and t. So first, let's get rid of this a prime. Okay, so I substitute in equation 3 into equation 2. I have 2t equals m a over 2. So t equals big MA over 4. Now I can substitute in equation 1. Into equation 1. Then we have little mg minus 1/4 big MA to replace t equals little ma. So now I can combine 1/4 big MA with little ma. Okay, and then we can finally get a equals little mg over 1/4 big M plus little a. Okay, so that's the acceleration A. And acceleration A prime is 1/2. 1/2 of little a. So we have mg over is plus 2m. When you divide by a by 2, okay, we'll get that. Okay, so that's one example that illustrate you the concept of the string. So for a string, for ideal string, the tension force is the same everywhere. Okay, so that's what we used here to draw the 3T's. And we also use the fixed pulley and movable pulleys, their properties. Okay, thanks for watching. Hello everyone. In this video, I will talk about the non-uniform circular motion in two dimensions. Now first, let's review what constitutes a non-uniform circular motion. Now in the RTZ coordinate system that we discussed in the previous video, let's say here's the circular motion center, and then the radial direction points toward the center. That's the tangential direction, and then there's also this z-hat direction perpendicular to the 2D plane. And we said that we should have the following. Along the radial direction, there's some net force sigma Fr equals MAR, which is given by mv squared over r. Okay, so let's say radius is r here. And along the tangential direction, the net force now should not be zero. It should be something that give rise to the AT. Okay, so equals MAT, and the non-uniform circular motion condition is AT is non-zero. Okay, so we should have some net force along this tangential. Now along the z-hat direction, we should still have a zero here. So there may be some force along this direction to balance each other. And that is the conditions or equations for the non-uniform circular motion. Now, under such a motion, the speed, of course, is not a constant anymore. The speed of the object will change throughout the circle. And that is actually implied by AT non-zero. Okay. All right, so let's look at one concrete example of this non-uniform circular motion. And I'm going to use this vertical circle. Okay, so here the circular path is along this vertical direction, and the radius of the circle is r. And then there's an object, suppose, for example, it's let's say a small block, okay, sliding up. And the surface here is smooth. Meaning that there's no friction to consider. All right, so now let's draw the free body diagram. The surface of the circular track should apply a normal force along this radial direction, and gravity should be in the vertical direction. And since the surface is smooth, so there's no static friction or kinetic friction. And that's it. That's the free body diagram. Okay, so let's write down the let's build the RTZ coordinate system, and then write down the three equations. R direction is along this radial, along the normal direction. Tangential direction is this way, tangent to the circular track. And then the z-hat direction will be in the horizontal direction. So I cannot draw it because right now it's vertical to the screen, right? So I can say z-hat is perpendicular to the screen. And in fact, we don't need to worry about this direction because both normal force and the gravity are inside the plane, so they have no component of their forces along this direction, along the direction perpendicular to the screen. Okay, so another way of saying that is when I write down that equation along the z-hat direction, there's nothing there. Okay. All right. So now along the along the R hat, along the radial direction, the net force equals the normal force is already along that direction. So let's write down normal force first. Now the gravity here, okay, has some angle with that direction, and I'm going to use this angle here. So let me first extend the radial direction, okay, and this angle, I want to call it theta angle, is the same as this angle theta. Okay, so now we need to consider like how to describe, how to introduce this angle theta. So now let's say when the object, when the block is here, the angle is theta equals 0. So that's likely angular displacement is 0. Equals 0 at this instant, and then later on at instant t, so that's t equals 0 second, we have theta equals 0, and then at instant t, we have theta angle, and that's this angle here. Okay, all right. So now with that, when I look at the gravity's component along this radial direction, it will be mg cosine. Okay, that's the cosine component of mg. And it's negative because it's opposite to the r hat. And that equals mar equals m v squared over r. That we want to calculate later on. Okay, now along the t hat, the net force equals, okay, so now we need the mg sine component, and that is negative. Okay, because the t hat direction is pointing along the increasing angle direction, right? Theta increases along this direction, and that is defined as positive direction, and then the gravity is pulling it down, so it's in the decreasing theta direction, so that's why it's negative. And that equals mat. All right, and so how to these are the two equations we have, and then now the question is how to solve at least the velocity information. What is the velocity? In terms of the velocity, we can say if I can find v equals vt, then that's good. But it'll be hard here for this problem. So we're going to just solve for v equals v as function of theta. So let's say we identify the angle theta for the block, and then if we plug in that theta, then we know its speed, and then that's also good. Okay, so let's try to find this expression. Now to do that, I want to do something here. I want to rewrite at as dv dt. Okay, so that's our definition of the tangential acceleration. It will change the magnitude of the speed of the velocity, sorry, and so that's why it's dv dt here. Now with that, I can I can do some integral here. So I want to integrate out the v, and then I want to integrate out this time or the angle. Now time would be difficult, so let's try to integrate out the theta here, the angle here. So what we have here is dv dt, and let me rewrite this as dv dv d theta and then d theta dt. Okay. Now the theta here, if I move it to the left side, then I can do the integral of angle theta. However, I introduce this d theta dt, so let's think about this first. D theta dt is omega, right? It's angular speed. But we also know that there's a linear speed and angular speed relation, omega equals v over r. Okay, so now if I apply that, I can change the variable omega to the linear speed v here, so that I can do the integral. Okay, so now I can let's cancel the mass first, and then I want to move the d theta to the left side together with the r here, and that's d theta, and the right side is v dv. Okay, now I can put an integral sign on both sides, and we need to certify that the correspondence is correct. So for example, at t equals 0 second, we can say the speed here is 0. Okay, so I'm going to start from 0 here. Oh, sorry, not 0. Some initial speed cannot be 0 because the block need to slide up. And at this instant, we have v here. Okay. Now for the angle integral, right, at t equals 0 second, the angle is 0 radian. And then right now it's at theta angle. So that's the integration bounds. Okay. Now let's see. The sine integral becomes cosine, right? Becomes cosine, but there's a negative sign, so we need to absorb that. So it's gr cosine theta. Theta goes from 0 to theta equals 1/2 v squared. So let's plug in the lower and upper bounds, and let's see what we get. So we have gr cosine theta minus 1 equals 1/2 v squared minus v naught squared. And if I rearrange these terms, I will get v squared equals v naught squared. So you need to move the v naught squared to the left side, so it becomes positive. And then we already multiply 2 on the left side, so plus 2gr cosine theta minus 1. Okay, so a bit of discussion here. So at any angle theta, this cosine theta becomes positive, right? Becomes positive, and it's less than 1. So this subtraction here, cosine theta minus 1, is negative. So you get a value of v less than v naught squared, right? So at any instant, it's less than v naught. So that's reasonable because the when the block slides up, it slows down. Okay. Now in the future, we'll also see that this equation is the same as the mechanical energy conservation. If we apply that, we'll get exactly the same equation. Okay. All right. So that's the one example of the non-uniform circular motion. And then we can actually talk about in detail the object's motion here. And right now it's like an arbitrary position. Now let's focus on some special positions. So again, here's the vertical track. And what are the special positions? So I'm going to talk about the bottom, the top, okay? These two positions. And we're going to study the requirement for the block to reach the top point. Okay, so that's the top, bottom. And then we also talk about at a position say here, the block falls off. Okay, so let's call this falling off position. Let's try to find this angle. So let's say the horizontal direction is this dashed line. Now what's this angle here? When the object, the block falls off. Okay, so let's talk about these three special positions, and then we'll be done with the non-uniform circular motion. Now at the top, first we need to draw the free body diagram. So I'm going to draw it here. So the normal force, the contact surface between the block and the track is above the block. So the normal force is going to push down the block. The gravity is already in this direction. Okay, now this direction is also the radial direction. Okay, and then there's nothing in the t hat tangential direction or the z hat direction, so we don't need to add to draw those directions. Now let's write down the Newton's second law along the radial direction here. So we have normal force plus gravity equals MAR. Let's also replace AR by V squared over R, so that's radius R. Okay, and then that's it. And then we want to find a special speed or the smallest speed, V minimum. What is this V minimum? So that V minimum, so that the block stays. The block can reach the top position. All right, so under that condition, we have normal force equals 0 at V minimum. Okay, so meaning that there's no pressure between the block and the track. So that's the signal for normal force being 0 here. Okay, so now with that, I get mg equals V minimum square over R. So V minimum equals square root of GR. Okay, so now figure out the minimum speed we need for the block at the top, so that it can reach the top without falling off. Now the bottom. Again, first the free body diagram. The normal force is upward now. Gravity is downward. And the radial direction is around the normal force. So that's why when I write down Newton's second law, I have normal force minus mg equals MAR mv squared over R. Okay, so now we don't need to talk about the such as minimum speed or maximum speed, because none of that will make the block falling out the track, right? So we just need to, for here, we just need to calculate normal force. So equals mg plus v squared over R. Okay, so now we can see, because v squared over R is always positive, so this term is always greater than mg. So when the block goes past the bottom of the loop, the normal force is greater than gravity. So that's the gaining weight. One example of this experience would be, let's say there's a car going over the bottom of a valley, let's say. Then the passenger inside the car will feel gaining weight in this process. Okay. All right, so let's talk about the falling off position. Falling off angle. How can I find this angle? Okay, so again, we need to draw the free body diagram. Remember, free body diagram is always the first step. Okay, so I'm going to draw first the normal force. That's along the radial direction. And gravity is this way. Sorry. And as I drew earlier, that's the radial direction. Okay. And then the angle here, that's the angle we're looking for, right? Now, to translate that into the angle that we need here to do the decomposition, let me first draw the tangential direction. Okay. Now this angle is theta, means this angle is theta. So you can write down the Newton's second law in the radial direction. It's given by normal force, the sine component equals MAR equals MV square over R. During the process of falling off the track, the normal force should be 0, right? So that's the condition that we must have here. Okay, so what we have here is mg now sine theta equals m v square over r. So that's the falling off speed. Square root of gr sine theta. Okay. Okay, so that's the falling off position theta, its relation with the speed at this falling off position. So now notice that the speed is not 0, right? It's not 0, so it's something finite. Now in the future, when we talk about this falling off position, again, using the energy conservation, then we can exactly calculate this angle. Okay. All right. So that'll be all for this video. Thanks for watching.